Right, so we got another question loaded up. For each relation below, identify the dependent and independent variables. Use a table of values to determine if it's a relation is linear, and then if it is linear, determine the rate of change. Okay, so a couple things that we can do here. First off, let's go and let's take a look at A. For A, we want to firstly identify the independent and the dependent variable. Okay, so A, let's actually make sure that we can make an A. First off, making an A. There we go. Okay. Afterwards, let's take a look at what I is looking at. Independent and dependent variable. So independent is always going to be our first column. So that's going to be our S's here. That's going to be like kind of our X if you want to think of it. And then our distance is going to be our Y column or our dependent. So we'll go with independent. Always our first column. And again, this is kind of like our X axis, if you want to call it, on a graph. And the variable that they have used is going to be S, and it is measured in kilometers per hour. This is going to leave our dependent, which we're going to kind of always think of as our Y column or like our Y axis or Y coordinates. They have chosen D to measure meters, so distance. Okay, so we got that one done. For A, use the table of values to determine whether the relation is linear. Okay, so to figure out if something's linear, we have to figure out how much each value is going up by, and it does look as though that each one of these values are going up by plus 10, plus 10, and plus 10. And it does look like each of our distance values or our Y values are going up by plus 7, plus 7, and this one is actually a plus 8. Okay, good. So for this reason and this reason alone, if these values all go up by the same, so 10, 10, 10, these values have to go up all by the same as well, and it does not look like they are. It looks like they're going up by 7 the first time, 7 the second time, but then actually 8 the next time. So I would classify this as not a linear function, since the independent variable to dependent variable, since the independent variable to dependent variable ratio is not the same for every change of value, let's say. Okay, so what I'm basically saying is the ratio that this is going up by 10 to the ratio that this is going up by 7 is not going to be the same for every value, because we see at the end this one's going up by 10, but this one's going up by 8. So this is not going to be a linear relation. Okay, let's take a look at the next one. So if the relation is linear, determine the rate of change. Well, we can't do that because it's not. And this is representing that the distance, I guess I should have read that before, the distance that's required for a car to come to a complete stop after its brakes are applied, called the braking distance. So it kind of makes sense. If you're going a faster speed, it's going to take you longer to stop, but it isn't a linear relation. So that kind of means that if you're going 50, it's going to take you this much. But if you're going, let's say, double that amount, let's say we're going something like 100 kilometers an hour, it would not take you just double the distance for that. It would actually take you quite a bit more time to actually stop your car. It would take a lot more distance for you to stop your car just than that. So it's not a linear relation. It doesn't go up linearly. If you're going very fast in your car, it's going to take quite a long time for you, or quite a long distance for you to stop your car. Okay, let's look at the second situation. Altitude of the plane, A meters, is related to the time, T minutes, that has elapsed since it started its descent. Okay, so let's kind of go back and let's do independent and dependent. We know that our independent is going to be that first column. Kind of think of it as their x values, but it's saying that their variable is t, and that's measured in minutes. Similarly, it's dependent variable. Dependent, thinking that as kind of like our y values, it is a. They've chosen the variable a, and that's measured in meters. Now let's take a look at our different values that we have. So as these are all going up, it looks like this is a +2, and it looks like that's the same. It's always going to be a +2 over here. Now for these values, it looks like it's going down 400, minus 400. It looks like it's doing that again. It is doing that again and doing that again. Hey, that's actually not bad. These entire things are going down by 400. So everything's going up by 2 on our independent side. Everything's going down by 400 on our dependent side. And as long as those are the same for both of us, this is a linear relation. Is a linear relation. Okay, I'll erase that. I'm sure somebody's thinking, why did I use pink for that? Is a linear relation since the ratio of change in independent variable and dependent variable. And you could say is the same, or you can say is constant. It is always going to be the same thing. Now, let's go ahead and let's do the last one there. So when we're talking about what is the rate of change? And there's a lot of ways we can do this, but what I'm going to do is just talk about the change of dependent. And I'm going to divide that by the change. Oh, actually, sorry. I just misspoke there. It's the change of, I'm going to say, I don't want to use dependent. I'm just going to say the change of, in our context, altitude. Change of altitude over the change of time. Dependent and independent would have been okay to use here. I just wanted to put it in the context of the question. So the change of altitude for each one was going to be -400. And the change of time between everything was 2 minutes. I'm just going to put my value over here of meters. So the rate of change here is going to be -200 meters over minutes. So it's going down 200 meters per minute. And I'm just going to write that in just explain that one. The plane is going down. Is going down 200 meters every minute. And that just kind of explains what the rate of change means there. Good. So biggest thing for us to sort of remember is that the ratio between our independent variable and our dependent variable has to be the same or constant through each number set, or through the change of every number set here. And if it's not, even for one value, then it can't be classified as a linear function. As soon as we have a linear relation. Sorry, we haven't talked about functions yet, but we'll see that we'll interchange those a little bit later on. So I'm just going to come back. Did I say, I don't think I said it anywhere except for right here. My mistake, I wanted to say relation here. Linear relation, and I did say it down here, so that's okay. But as soon as we do have a constant change of our independent to our dependent, that ratio, then it is going to be a linear relation. And we just wanted to be able to explain that that change of altitude going down our list is going to be -100. And the change in our list in our independent variable is 2. And then we want to just relate that. 400 meters divided by 200 meters, -200 meters divided by, or -200 meters per minute. And that's really how we describe that in English. The plane is going to go down 200 meters every minute. And that's our rate of change.